This class, we're going to talk a little bit more about the drinking water treatment. So if you do a quick recap of our last class, so last class, we mainly talked about different types of water for extracting the drinking water, right? There's underground water, there's also surface water. So we said that underground water or the groundwater are generally cleaner, but they have the issue of hardness, right? Mainly because there are minerals getting dissolved into the water. And those minerals are hardness ions, like magnesium ion or calcium ion. And when you boil the water, you're going to find those white scales. And then for the surface water, we said that since it's closer to the human environment, right, we're going to see more pollution, either the organic pollution or the pathogens, or sometimes if you have, let's say, other types of trash, right, when you dump it into the river, you're also going to increase the turbidity of the river water, right? So in that case, you will need more treatment processes to deal with these contaminants. So we also know what are the federal standards, right? The MCL and MCLG. So this MCL is reinforceable standards, right? If the water quality failed this standard, then there will be some punishment. And there's also MCLG. The G here represents goal, right? That is our goal. So that's why it's not reinforceable. Okay, so in this way, these are kinds of like the target, right? It doesn't matter if the water treatment plant didn't reach that target. And then we discussed different types of water treatment methods, right? There's screening, coagulation, flocculation, sedimentation, sand filtration, disinfection. And then for the underground water, you have the softening process. And here for the top 5, this is basically ranking them based on their sequence, right? We have the screening to remove the larger chunks of materials, right? Coagulation, flocculation tries to basically change the very small particles in the colloid or in the turbid water into larger chunks of particles so that they can settle down. And then you have the sedimentation, which basically remove these larger particles just based on their gravity. You have sand filtration, which can remove the remaining smaller particles, right? And then disinfection is the process where you add chlorine into the water to further, let's say, basically you need to have some residue chlorine in the water before we distribute it into the households. Okay, so if we carry on this from this coagulation flocculation process, so basically it's a process in here, right? The method we remove these turbids or the turbidity in the water is by adding the coagulants. So last time we said that the colloid systems is very stable, right? Basically that's the components that's in the water that giving you this milky types of texture, right? So they're very stable because these are all suspended, very small suspended particles. Their size is too small. So if you count on them to, let's say, settle down by gravity, it's going to take a very long time, right? And there's also other reasons. For example, yeah, the first one is their size is too small, right? Secondly, is because these particles are negatively charged. We said that it's mainly because some of the silicon ions are substituted by the aluminum ions, which give the particles a negative charge. And if they have the same charge, then because of the repulsion, they will not coagulate, they will not form larger particles, so they will just suspend in the water. And then the third reason is the Brownian motion. So the Brownian motion is just a random motion of these small particles because they are always colliding with the water molecules. But because they are small, so I would say their mass, they can still feel the collision of the water molecule on them. So if there's a momentum transfer, right, if there's a collision, then it's going to give a tiny movement of these particles. So basically, it's giving a random motion of these particles, and they're pushing the particles moving around. So it's further more difficult to let these particles to form larger particles. All right, so they cannot settle down from the water. And that's why we have these coagulants. So the role of these coagulants is to neutralize the surface charge. And since these particles are negatively charged, so if we have ions that can carry multiple positive charges, then they can attract these tiny particles together. And then when they are in contact, they stick together and then form larger settleable size. So I think last class, when I introduced this process, this coagulation flocculation process, I used the wrong sequence. So basically, they should start from the left. Okay, so on the left, you have this more turbid water, right? And this is after you put in the coagulants. So you can already see these tiny dots here, right? These represent the tiny particles that already started coagulating. And then as they further collide with each other, you can form these larger particles, further larger particles, right? And when they're at this size, it's already relatively easy for them to settle down just based on gravity. And then in the end, you get more clear water compared to the beginning. Okay, so last class, we also showed this effect of these different types of ions, right? You have basically for aluminum ion, you need a smaller dosage to bring down the turbidity, right? Compared to the other types of ions, like the calcium ion or sodium ions. And then we also said that when we treat the water with these coagulants, actually, the chemical reaction brings basically more available of these hydrogen ions. These hydrogen ions will increase the acidity of these treated water. So that's why after we add these coagulants in the water, we need to further add alkalinity to neutralize the acidity, right? Especially for drinking water. We cannot have this high acidity because they're going to corrode the pipes for transporting the water. So people normally use the lime or soda ash to deal with the water. So this is about the mechanisms, right? These are the chemical reactions. So how do we achieve that in the engineering perspective, right? So here you can see that basically we're separating them out into a coagulator and a flocculator. Okay, so this is a two-step process. It is not happening just in one reactor. So the main reason is that there's different needs for, let's say, the reaction and different needs for settling. Because if you think about the process where we dispense these coagulants, right? So we're basically adding something like a reservoir here, and then add the coagulants, the lump into the water, right? To suspend these coagulants into the water, if you think about the process, do we prefer a faster process to suspend the chemicals, or do we prefer a slower process to suspend the coagulants, right? We prefer a faster process because we want these aluminum ions to distribute evenly in the water, right? If we have a very slow process, then they cannot be very evenly distributed, right? You're going to have a higher concentration at certain location, a lower concentration at other location. This is not uniform distribution, right? If you don't have a uniform distribution of the coagulants, then you don't have a uniform treatment of these colloids, right? So that's why we prefer a faster mixing. And also we prefer a shorter residence time for the water flow in here. And that's mainly because once you put the coagulants into the water, then the ions or the colloids start to coagulate with each other and they try to form larger particles. But if you have a very long residence time in here, and then since you have a rapid mixing, which means that you have a faster turbine in here, they're just going to break these flocks apart, right? They're just going to break these larger particles apart if you let the water to stay there for a very long time. So that's why for this coagulator here, we prefer a faster mixing and a shorter residence time. Well, for the flocculator, for the flocculation, this is a process where we are forming these larger chunks of particles, forming these flocks. So under this situation, we would prefer a, let's say, a slower mixing, right? Compared to the coagulation, because here we still need some mixing because the coagulants might not be uniformly suspended here, right? We still have these, let's say, the blades here to stir the water, but without the fast speed to break down the flocks, right? At the same time, you need a longer residence time. So that's why the flocculator has a larger volume, right? So you need a longer time for these particles to gradually collide with each other and then form those larger particles so that they can settle down, right? After they settle down, they can go into the sedimentation basin to just let the particles to further get removed based on their gravity. Okay, so now let's look at the design considerations for the coagulator and flocculator. So first, about the coagulator, right? As we said, we need a rapid mixing of the coagulant. Okay, So let me change that to, yeah, the pen is fine. Okay, so we said that we're going to need a more rapid mixing of the coagulant, right? So the reason is that we want to disperse these chemicals to particle surface, to the particles for the charge neutralization, right? So that's why people normally use these shorter blades, right, or the turbines or propellers, right, to mix the chemicals and then rapidly so that they can get uniformly distributed into the water for treatment. And more specifically, people design or define this parameter called the degree of mixing or the velocity gradient. Okay, so this G here. So G is the dV divided by dx. So basically, this is the gradient of the velocity of this blade here as a function of the location, right? So basically, if you think about this, let's say this turbine here, okay? So if you calculate the dV dx, so it's basically just the velocity divided by r, right? So when I mean the velocity, it is velocity at here at the end of the turbine, right? And then the r here is just the radius, okay? So if you consider its unit, right, the velocity has a unit of meter per second, and then the r, the radius, has a unit of meter, right? So then you're going to have a unit of inverse second. Okay, so generally for the coagulator, we will use these mechanical mixers that has a velocity gradient of 7 to 1000 per second. Okay, so how large is this? So easy way to think about it is to, let's say we can find the size for this R here. Okay, so for let's say generally for the propellers, okay, so we can think about a really smaller propeller, but even for smaller propellers, they will probably have a radius of half a meter. Okay, so let's say 0.5 meter. Okay, so if they have a radius of 0.5 meter, right, if you plug that in, the velocity will become around 350 to 500 meter per second, which is very, very large. Okay, so if you think about 500 meter per second, it's already faster than speed of sound. Okay, this means that there's a very, very rapid mixing in this process here. And also about the retention time. So we said that the retention time is basically the residence time of the water in any reservoir or any container there, right? The retention time is just 20 to 60 seconds. Okay, so it's within a minute. So based on the retention time, actually, we can also evaluate what is the size for this coagulator here. So if you recall, I think when we discuss the PFR or CSTR, right? So we also define this retention time, that theta value, right? That theta or that time factor or time parameter is just the volume of the reactor divided by the flow rate. Okay, so the volume is the total space. The flow rate is how much volume is going through by or per second. Okay, so that's why we can have the volume just equals the time multiplied by the flow rate. Okay, so if you know the time and if you further know what is the flow rate going through this coagulator, you can estimate what is the volume of the reactor. For example, if you have a flow rate of 1 meter cubed per second, okay, 1 meter cubed per second. And then if you have a retention time, let's say 60 seconds, then it just means that the total volume is 60 meter cubed. Okay. But 60 meter cubed is a relatively small volume. Right? If you think about a container that has let's say a depth of 2 meters, then it just means that the surface area is 30 meters, 30 meters squared, right? That's just a 5 by 6 let's say surface area. Okay, 5 meter by 6 meter, that's a relatively small space. Okay, so that's why for the coagulator, we just need a smaller volume, right? And then we also, that is because we have we require a smaller or a shorter residence time. Okay, and there's also rapid mixing going on. What about yeah? So what about the actual designs? Okay, so these are the actual designs for different types of the coagulators, right? You can have these single turbine reactor, right? You can use the blades, or you can use these channels, or you can use these blades. You can have 2 channels or 2 compartments, right? Different types of processes, but they all satisfy the requirement that you need a very large mixing speed, right? Or basically a faster mixing, right? And also a shorter residence time. Okay, so what about flocculation? Okay, so flocculation, as we introduced, we're going to have a slower mixing, because if we have the faster mixing, then we're just going to break those flocks apart, right? So we spend all of those efforts to bring the smaller particles to the larger particles. If we have a faster mixing, they'll just break apart again. Basically cut by those turbines. Okay, so this is to allow the particles to form these larger flocks, right? And then also avoid the flocks being broken or resuspended. So that's why if you look at this G value, this is the velocity gradient. Again, that's, you can think of that as V divided by R. Okay, so this G value is just 30 to 60 per second for a flocculator. If you compare that against the coagulator, you can see that this is much, much smaller, right? So if you have a half a meter radius turbine, right, this just means the velocity is 15 to 30 meter per second, which is much slower. And then for the residence time, you can see that this is also talking about different orders of residence time, right? This is 15 to 45 minutes. Okay, so because of this longer residence time, if you think about this, volume equals Q multiplied by T, right? QT. So we said that basically the volume of the tank or the reservoir is just a product of the flow rate multiplied flow rate and the time, right? And then for the coagulator and flocculator, since they're directly connected, right? So their flow rate is going to be the same, okay? So their volume or the ratio of their volume just depends on the ratio of their residence time, okay? So you can see that actually this is, for this section, this is the paddle flocculators. So you're still using the turbines, but since you don't have a requirement for fast speed, you can just use the paddles instead of those round shaped, instead of these propellers, right? You can just use paddles that look like this. Okay, so basically here, based on this relationship here, you can already imagine that there's going to be a large difference in terms of the volume for the flocculator. So we can have these paddle flocculator. We can also have the baffle channels. So what happens in the baffle channels is that instead of using a rotating part, we can just create different channels that can let the water to flow or elongate its residence time. Okay, so for example, here you can have a reservoir that looks like this. Okay, so if we draw out the 3-dimensional shape, it's going to have a cubic shape, right? But within this reservoir here, you have these horizontal baffles, horizontal channels, so that the water is constrained to just flow from top, right? And then go through these again, and eventually to the end. Okay, and then we can also have the baffled channels that look like this, right? The water has to go again, and then going to here. So basically, in this way, we can elongate the residence time, because if you don't have this channel, if you don't have these baffles, then let's say if you just have an empty reservoir here, then the water will just flow in this direction, right? But by having these channels here, you're constraining the water to go through this longer distance so that you can have a longer residence time, right? But the thing here is that you don't have a moving part to further mix the water, right, for further dispensing these coagulants, right? So I would say this is for probably designed for some treatment that has a better mixing in the coagulator. Okay, if you already have a better mixing in the coagulator, where you have a faster moving turbine, right? Maybe at the end, we don't need these moving parts here. So there's also this paddle flocculators, right? The paddle flocculator, basically you have a paddle inside, right? You have a center shaft, right, to turn the paddles, right? Here you don't need those blades because you don't need a faster mixing. And then you can also have these horizontal paddles, right? So they can also get separated into different chambers. But the main idea is that we need a slower mixing and then at the same time a larger or longer residence time. Okay, so this is the difference for the coagulator and the flocculator. So here, this is a short question, or we'll say this is a short quiz. But since we're having this class in a recorded session, so maybe you can just quickly go through this, right? So compared to the coagulation, a smaller g, or this velocity gradient, is used for flocculation. Why is that? So there are three options to destabilize particles to prevent breaking up flocks or to save energy. So the correct answer should be B, right? We don't want to stabilize the particles. We just want them to gradually form these larger flocks and then settle down by themselves. Okay, so we want to prevent the breaking of the flocks. All right. So then that is the coagulation, flocculation, and then after these flocks are getting removed, some of them will settle down onto the ground, right? There are also already larger particles that they can go further into this sedimentation basin. So basically, the sedimentation basin will further remove the particles just based on gravity, right? This using this sedimentation term here. So how do we design the a sedimentation basin? Okay, what are the design parameters? How do we consider this process? So basically, you can treat this sedimentation basin as a cubic tank. Okay, so you're introducing the water from one side and then let the water exit from the other side. What happens is that for the particles that have larger sizes, then they're just going to settle down by gravity, right? If you think of the extreme condition, let's say the ideal condition, if the particles are too small, then they cannot settle down, and at the end, they will just exit from the right side and then exit. Okay, so now let's think of the extreme condition. Okay, so the extreme condition will be, or the let's say the smallest particle that can get settled. Okay, so for the smallest particle that can get settled, then they will have the longest trajectory. They will probably get introduced from here, right? So after they're introduced into the tank, there can be some turbulence. They will arrive at this location and then start to settle down. And then since they are the smallest size of particles that can get settled, so they are going to go through this diagonal trajectory and then settle down at here. Okay, so for particles smaller than this size, then they will just go above this location and then exit. For small particles larger than this size, then they will settle down along this trajectory. Okay, so in this case, what we can do is to just, let's say, find out a special cut size or special cut velocity for these particles, right? So we can tell the water treatment facility, let's say, we just want the particles, want to remove particles that can settle faster than 1 meter per day. Okay, so let me write this out. So for example, we can just specify a velocity, right? For example, we can make it 1 meter per day. It can be any value, right? So if we want to remove smaller particles, then we want to make this cut velocity to be a smaller, have a smaller velocity, right? Because smaller particles, they can settle down with a smaller speed, okay? And then how does this velocity relate to the dimension of this sedimentation basin? Okay, so here I already have the equation, but you can also think about it in some like more physical way, right? So if you think about the trajectory of this particle, so they're settling down from this location to this location, right? We said that this velocity is a vertical velocity, right? That has a settling velocity of a certain value, right? This vertical velocity, if you multiply that by the residence time of the water in the tank, then they're just going to be equal to the total height of this tank. Okay, so basically you're going to have this relationship of, let's call it V naught, and then you multiply that by T, then you're going to get H, which is the height of the tank. Okay, so further, let's separate the V naught here. So V naught is is H divided by T. Okay, and then we know that the T here, this is residence time, right? Or the retention time. The residence time is velocity divided by Q. Okay, so that's not the velocity, the volume of the tank divided by the flow rate going through the tank, right? And then you have this H here. And further, for the volume of this tank here, the volume is actually the surface area of this tank. So to draw that out, the surface area multiplied by the height. Okay. So you have Q. If you move the Q to the numerator, right, you're going to have H Q. And then for the volume, you have H multiplied by A. Okay, so the H got canceled. You just have Q divided by A. Okay, which is the equation showing here. Okay, so here there are extra terms, this length and width. So basically, I'm just converting the length and width to the area, right? So length is like this dimension here, right? This is length, and then width is the dimension that's going into the screen, right? So yeah, we can just convert that to A, and this is exactly what we get. So basically now we are relating this velocity to the dimensions or to the operation of this sedimentation basin, right? So the Q here is the flow rate, the A here, this is the surface area, okay? So now let's say we talk to the water treatment facility, okay? So we want to remove particles that can settle down with a speed that's faster than, equal or faster than 1 meter per day, right? And then what does that mean? You will put in this value, you know what is the flow rate this water treatment facility is handling, then you can calculate what is the surface area that's needed, right? So this water treatment facility, they can start to build their sedimentation basin that can satisfy this settling velocity. Okay, so we have been calling this term as settling velocity, but actually it has a special name called the overflow rate. Okay, so it may sound a little bit weird because we're talking about the velocity, but this is using a rate. Okay, so it's not flow rate. Okay, flow rate will have the unit of meter cube per second. So the overflow is separated from the rate. Okay, so this is a unit. This is a velocity term. Okay, so here I also have the overflow rate or the settling velocity is designed by the treatment facility. So basically they will determine a critical overflow rate or the settling velocity that they want to remove. Okay, so for the particles that has a smaller settling velocity or the smaller overflow rate, they won't care about it because those particles will get removed by the filtration or the sand filters. Okay, so again, for this process or the sedimentation process, you can see that this is only talking about, or we're only trying to remove particles that has a settling velocity greater than a specific value, right? We further derived how this settling velocity is related to the configuration of the water treatment facility. Okay, and then based on that, you can do some design calculations. Okay, so here we have a problem, we have an example problem. Okay, so it is talking about a water treatment plant that has a flow rate of 1 meter cube per second. Okay, so this is the value that I used. And it uses 10 sedimentation basins. Okay, so basically instead of having one, they're having 10 of them. So basically you're splitting the water flow to 10. Okay, and it specifies an overflow rate of 50 meter cubed per day per meter squared. So first, if you look at this value here, you may feel is a little bit terrified, right? But actually, if you cancel the unit here, you're just going to get meter per day. Okay, so it's just a velocity term. What should be the surface area of each tank? Okay, so basically, what we can do is first we can use this relationship here, right? You have the V naught equals flow rate divided by area. Let's say we just call this area as A total. Okay, So if you plug in this value here, right, this is 50 meter per day. Okay, and the flow rate is 1 meter cube per second. Right, you can move this total area to the left-hand side and then divide flow rate by the velocity. Okay, but one thing you need to pay attention is that here that it's using the day and here it's using second. Okay, you need to do a unit conversion. For example, you can convert the flow rate to how much volume per day, right? This would mean you need to multiply by 3,600 and then further multiply that by 24. It's 24 hours per day. Okay, so that's going to be this amount of flow per day. Okay, and then you just basically first, let's say you get A equals Q divided by V naught. Okay, so you can just plug in this value in here and then divide that by 15, right? Divide this value here. Let's see. Move this value here. And then in this way, you can calculate what is the total area, right? And you have 10 of these sedimentation basins, you can just divide this total area by 10. Another way to think about it is since you're splitting the flow into 10 different branches, right? And actually, instead of calculating the total area first, you can just divide or calculate what is the flow going to each of the basins, right? If you have 10 of these basins, you just divide the flow rate by 10. Okay, you divide that by 10, and then you can get the surface area for each of the tank. Okay, so that is the consideration for dealing with this sedimentation basin. Okay, the equation is quite simple, right? It's just for 3 parameters. You can do conversion from one to the other, right? But things that we can derive it just based on the setting of the particles. So that's the physics in here. Okay, so after the sedimentation basin, as we said, we're only dealing with particles of a specific settling velocity, right? There are particles that has slower, right, or the smaller settling velocity. So these particles will go through this sand filtration system. Okay, so for the sand filtration, here I have a schematic diagram. So what happens is that you're just introducing these treated water into this sand filter here. Right, you have the different layers of materials. You have the sand at the top, and then you have the support gravel. So basically, support gravel are harder materials, right? They can support the sand because sand itself doesn't have a very strong mechanical property. If you don't have this support here, then you just get a slurry of sand and water, right? So that's why you always need to add this layer of the support in here. Okay, so they can remove the smaller unsettleable solids, and this is mandatory for the surface water and the shallow groundwater. Okay, because there are suspended solids, right? There are turbids, and if you think about the particles that we that are introduced here, there will be some, let's say, suspended solids that are already in there. And since the coagulation flocculation process also generate these suspended solids, right? So it's going to be a mixture of them, and we have to deal with them with the sand filtration as a last step to remove the suspended solids. Okay, so there are different types of filtration principles for sand filtration. There is straining. So straining means that the particles are just too large to pass through the sand media. Okay, so you can think of that as a sieve, right? So if you have larger chunks of materials, they will just get blocked, or the screening process, right? So this is the straining because the particle is too large. And then there's also interception. So what the interception means is that when the particles are passing through this media here, if they have a smaller size or medium size, once their surface get in contact with the surface of the sand particle, they will just get attached in there because of the van der Waals force. Once there's a contact, they will just get fixed over there, right? There's also flocculation. So the flocculation means that the particles are capturing each other. Okay, so you have a larger, let's say a longer chunks of particles, and if the particles pass by, instead of getting captured by the sand particles, they're just getting captured by these suspended solids that you already deposit in there. There's also a sedimentation. Sedimentation is just the gravity, right? The particles are too heavy, right? They just settle down by gravity and then get collided in there. Okay, so these are the 4 different mechanisms in terms of the sand filtration. But overall, to calculate this this removal of the particles based on sand filtration, we're just still going to use some simple equations. Okay, so if you think about the process of the particles getting removed or getting filtered by the sand filters, you can see that initially the particles are getting retained on the top layer of the media, right? Because they're getting contact with the top layer of the sand. Okay, and then after a while, the water velocity increases. Okay, so the reason for the increase of velocity is because you're already blocking all of these pores, right? You have a narrower pore size, and then the velocity is going to be larger. Okay, so once the velocity is larger, right, you have a basically a stronger force to directly impact onto these particles, so they break the particles apart, and then force these particles or smaller particles to start penetrating deeper into the sand. Okay, so but eventually, if you have a operation or have the operation of the sand filter for a long time, then this system is going to collapse, or basically at the state of before it really collapse. Okay, so then some of these particles can get suspended into the stream of the treated water. Okay, so basically you're going to see a increase of the turbidity for the effluent. And under that situation, you need to take this filter offline and start to introduce the backwashing process, the backwashing water. Okay, so you're going to use a cleaner stream of water, right? So basically what we do is we're going to shut off this inlet here or inflow here, and then create an effluent on the top. Okay, so the backwash water is going to bring all the particles, right, flush them out, and then bring to the effluent. So in this way, you can remove the particles that are already in the sand. Okay, so in this way, you can regenerate the sand filter, and then it can get back online. So since we have this backwashing process, if you think about the real operation of the sand filter, then we cannot just have one of the sand filter, right? Because the water treatment process, this is a continuous process. Okay, and if we have the backwashing, it means that during the backwashing, we cannot introduce any of the water to the sand filter. Okay, so that's why normally when we construct these sand filters, we'll just build multiple of them. Okay, so we'll build replicates, right? There's branch going through each of the sand filters, and then you're going to use the backwashing one by one. Okay, so you cannot do the backwashing for all of them. Otherwise, you cannot get any continuous flow of the water. So you just take them offline one by one. Okay, so because of that, there will be some design considerations for different types of sand filters. Okay, so as we said, for the sand filters, if you think about its operation, although there are different mechanisms, but in terms of operation, it's still a pretty simple design parameter. Okay, so this is the loading rate. So actually, the loading rate is another velocity term. Okay, so it is just the flow rate divided by the surface area of the sand filter. Okay, so if you think about the design of 2 different types of sand filters, let's say they had to handle the same amount of flow rate. Okay, so one with a broader, one with a wider sand area, one with a narrow sand area, the filter area, right? Then the velocity that's going through the sand layer is going to be different, right? You have a slower velocity through the this wider or larger system. You have a faster velocity going through this narrow system. So which one is going to be more easier to have, let's say, the penetration of the particles, or which one is easier to get collapsed? It's going to be the narrower one, right? So that's why this this loading rate, or this what people call this phase velocity, is a critical parameter when we are trying to design these sand filters. We cannot let the loading rate to be infinitely large, or otherwise it's just going to damage the system. Okay, so the loading rate is also dependent on different types of filters we're using. Okay, so if it's just a single layer of sand, okay, so it cannot handle a very large loading rate. But if you can find other materials, okay, so for example, different layers of materials, right? Let's say layers and layers of materials on top of the sand, so that you can distribute the particles into different layers, then you can have a faster loading rate. So we can start from the simple media rapid sand filter. This is just a single layer of the sand. Okay, so basically for this type of sand filter, you can only allow a loading rate of 235 meter cubed per day per meter squared. Okay, so this is still a velocity term because you can cancel the meters, right? And when people build these rapid sand filters, we need to have at least 4 units to just think about the water backwashing, right? So because we need to take some of the filters offline. And also the size of each filter is up to 100 meters squared. So then you might wonder, why do we have a larger, like a constraint on the maximum surface area? Okay, so the main consideration is that if you have a very large sand filter, then the distribution of the sand is not going to be uniform. There's going to be a location where we have a thicker layer of sand. There's going to be a layer or a location you have, let's say, lower, shallower distribution of sand, right? So under this situation, then most of the water is just going to go through this location, right? So you cannot distribute the water uniformly. So that's why there's also a constraint on the upper limit for the sand distribution. So there's also process for backwashing. You can pump the water back and then get particle removed. And normally the backwash water just use 2 to 4% of the treated water. Okay, so this is a single media rapid sand filter. There can also be multiple media or the multimedia sand filter. Okay, so the consideration is that if you think about the particles getting collected in the sand, basically in the top layer, you're going to have a lot of larger particles, right? Because the larger particles, they're also heavier in size, right? But for the if you consider deeper in the sand, you're going to have a lot of smaller particles because they can penetrate further into the sand layer. So if you think about the mass of the distribution of the mass in this sand layer, so top layer is going to be much heavier, right? Because you collect more larger particles in here, right? And then the lower layer is going to be lighter. And this is not a stable structure, right? If you have a very heavy top, right? So in this way, or because of this, people actually add multiple layers on top of the sand. For example, you can use the anthracite. So anthracite are basically larger grains of sand that has larger pore size. If you have larger pore size, then you can block these particles further up. Okay, you can block them here. So before they get into the sand layer here. So this is going to be a more stable structure. And because of that, so basically you're going to have the largest and lightest on top, right? So because of that, you can increase the loading rate up to 300 meter cubed per day per meter squared. Okay, if you compare that against the single layer sand filter, you can see there's an improvement in there. Okay, and for backwash of these multimedia filter, you can use air and water mixture to basically better mix them. Okay. So this is about the multimedia filter. And then for the design considerations, let's say for the single media rapid sand filter, we said that we have to have at least 4 units. Okay, but overall, when we design these rapid sand filters, we want even number of filters. Okay, mainly because when we build these filters, right, when we distribute the water through a major pipe, we just want to, it's a lot easier if we just build them in parallel, okay, which can distribute the water more evenly. Okay, so in this case, we want even number of filters. And then, so also we need to make sure that the filter loading rate should not be higher than the maximum loading rate. For example, here, the single media rapid sand filter, you cannot let it increase to higher than 235, right? For multimedia filter, you cannot let it be higher than 300 value, okay? So here is another example problem. I think we can probably end this class here, right? Because we didn't spend a lot of time for you guys to go over these problems here. So you can, when you go through the recording, you can just hit pause and then do the calculations. So let's take a look at that problem. So we have a flow rate of 0.8 meter cubed per second. So it asks for what is the number of rapid sand filter boxes that has a dimension of 10 by 10 and has a loading rate of 110 meter cube per day per meter squared. Okay, so we have the loading rate, right? The VA, that is 110. Okay, and then this is, let's just use meter per day. Okay, so according to the equation, we have the VA equals the flow rate divided by the surface area. Okay, so here, this is the total surface area. Okay, so the flow rate here, you have, so for the flow rate here, you have the value of 0.8 meter cubed per second. Okay, so then with these two values, okay, so with these two values, you can calculate what is the total area. Okay, and also you need to think about the conversion of the day here. So once you have the A total, you can divide the values by the area of each of the sand filter, which is 100 meters squared. Okay, so A each. Okay, so you can find out that actually the value is 6.28. So now this is the engineering part. So how should we design the system? Okay, so you have 6.28. So should we round it down? Actually, no, because if we round it down, then we cannot make it. So we cannot make the 6, because if we round it down, then the loading rate is going to be higher than 110. Okay, so basically it's going to be higher than this specified loading rate, although it's still lower compared to the maximum loading rate, but we don't, since this problem already specified the loading rate, right? We cannot make it smaller than this value. Okay, so that's why we need to round it up. We'll round it up to 7, but 7 is not the end yet. We need to make it to further to 8. We need to make it further to 8, and then so basically you have even number of the filters. Okay, and then we can satisfy this problem, satisfy this requirement. Okay, so basically this is a design considerations, right? So we have to use these different standards and then different methods, and then find out the optimal design consideration for these systems. Okay, so I think that's it for this class, and I'll talk to you guys on Thursday, right, to further discuss about the water harness and how we can remove that. Okay, just feel free to let me know if you have any questions. Thank you.